So, welcome student to the next class of nonlinear optics and its application. So, in the previous class we have studied two different principles. One is Newman's principle and another is Kleinman's symmetry, and applying these two symmetries we find that it is possible to reduce the elements of D matrix, and eventually from 18 different elements we can go down to 10 different elements, and then further we can even go to two different elements, two different distinct elements, and making all other elements as 0, and that one can find by applying Newman's principle, which suggests that under symmetry operation the structure of the D matrix remains same. So, today we will going to understand the more important thing, that how inside this crystal the second harmonic process is generated. So, let us see what we have today. So, in order to understand the second harmonic in the crystal, first we need to know what is the matrix form for second harmonic, and then sum frequency generation and difference frequency generation, and then we will study about the second harmonic generation in a specific crystal. We use Credipi crystal here, which is a very well known crystal to generate second harmonic. So, let us start with the matrix form. So, this is not a very new thing, but still this matrix form is important and one should understand that how these matrix forms are generated. So, in couple of classes ago we have already demonstrated that how the P matrix is represented in terms of ijk, and this P nonlinear in terms of ijk is written in this way as shown here. So, this is the way one can write. Since we are dealing with second harmonic, so my frequency component will be 2 omega. So, 2 omega is generated as a result of the combination of omega and omega. So, once I add 2 omega, I will generate the frequency 2 omega. This is the 2 omega frequency component of the nonlinear polarization. In general, in nonlinear polarization there will be many other frequency terms that we have already shown in our earlier classes, but here we are only looking for those terms where the frequency components are 2 omega. Now, the frequency component of the 2 omega can come from these two elements Ej and Ek with omega and omega. So, when they multiplied each other, so we will have a 2 omega components, and that is why here we are saying this is a second harmonic process. So, eventually in terms of D matrix we will have this. So, once we have this component form, now it is necessary to write in a matrix form, because at the end of the day what we have this D matrix in our hand. So, we know what is D11, D12, most of the cases as I show in the previous classes that it is vanishing, most of the components are vanishing. So, we will have a simplified form of the D matrix, and then it is easier for us to calculate Px, Py, Pz, which are the nonlinear components of polarization matrix. So, now if I write these things in matrix form, then Px, Py, Pz can simply be represented in terms of Ex, Ey, Ez in this way. So, one can readily derive this from this. So, if I write Px here in the right hand side, in the left hand side it will be 2 epsilon 0 d of x, and now ij is the indices that will going to change. So, first indices will be xx. So, I will write Ex, Ex. So, that is E square, this is the E square term, and this is the D11 index. Xx index means D111, and we know that D111 means D11. So, if I multiply, the first term is this. What about the second term? Second term again in the left hand side Px, we have 2 epsilon 0 D1, second term should be D22. If I write D22 in the second term, we will write D, here 2 means yy, so it should be dyy. So, we will have D2 D12 Ey square. So, this is D12 Ey square, the second term. Similarly, for third term we have D133 and we have Dezz, so it is z square. Fourth term we have D, for the fourth term which is D14 here, which is d of 1, 4 means 2 3, 2 3 means if I write in terms of x y, so it is x y z. So, here we have e of y, e of z, and this will come twice because this is y, this is z. So, another term will come where we should have this is z, and this is y, but both the cases we know for the permutation symmetry that d of x of y z is equal to d of x of z y. So, we should not bother about that. Since there will be 2 term, so 2 multiplied by e y e z will be here corresponding to d 1/4 term. In the similar way, d 1/5 and d 1/6 we have all the terms here. So, this is for p x. In the similar way, we can write p y and p z. I do hope all of you understand how to write this matrix form, which is very important in studying how the second harmonics are generating inside the crystal, and the process is quite straightforward. Once you know what is the component you are talking about, then you can readily able to write, and this is the compact form of this. If I expand this, it will be coming in this way only. Okay, so this is the matrix form of the second harmonic. So, we can also able to write the matrix form of sum frequency generation. So, sum frequency generation is nothing but if we have two frequency components, then what happened that these two frequency components can add up and generate a summation of that we know because we have already studied these things. So, omega 3 is a frequency which is generated by omega 1 and omega 2. So, now p ith component can be represented in terms of E j and E k having the component omega 1 and omega 2. In the similar way, if I start with p x component, it should be x and x, but the frequency components are different. You should note previously it was E x s square, but it is now x x, it is now y y, but the frequency components are different, and z z frequency components are different. Once we go to the other term, then again we have the combination, one combination, for example, the fourth term. So, d 1 4 is essentially d 1 2 3, d 1 2 3 means d x y z. So, once x y z is there, this is x, this is y, this is z. So, we will have two terms, one is y with a frequency component and another is z with a frequency component 2, but other term is still possible, which is y with a frequency component 2 and z is a frequency component 1. Both the cases they will going to generate a frequency omega 3, because when we multiply these two things we will generate omega 1 plus omega 2. If we multiply these two, again it will generate omega 3, which is omega 1 plus omega 2. That is why we have two terms adding here. In the similar way, we have the other terms, exactly the logic is same. So, this is the way of writing of second harmonic for sum frequency in matrix form. Well, if I able to write the second harmonic and sum frequency, so why not the difference frequency? So, difference frequency one can also write exactly in the same form, but one should remember that since it is the difference frequency generation, so we have p x. So, I need to find out omega 3. Omega 3 is how omega 3 is generated? Omega 3 is generated as omega 1 minus omega 2, the difference between these two. So, since it is related to minus of omega 2, instead of having E k omega 2, I should write E of star of E k of star of omega 2, because we know that this is E k star of omega 2 is nothing but E k of minus of omega 2. So, this notation in many books you will find they follow. So, we are following the same notation here. So, now instead of multiplying these two, we now have a star. Here also in the similar way we will have the summation, but in form of star, because we are dealing with difference frequency generation. So, these forms are very important. So, I believe you can understand these things. Once you once you write this matrix form, readily we will find what is the value of Px, Py, Pz. That is important because these are the terms that is generating the second harmonic waves. So, that is why the direction is important, in which direction they are generating the second harmonic wave or the sum frequency wave or the difference frequency wave is important, and one can find out the entire thing by just writing this matrix form. Well, after having the knowledge of this matrix form, the next important thing that we going to learn is about the KDP crystal. KDP crystal is a very interesting crystal, and in KDP crystal normally we generate the second harmonic, and let us try to find out what properties we have in KDP crystal. So, KDP crystal is a uniaxial crystal, transparency in the visible range. Obviously, it is transparent. If it is transparent in the visible range, then it is easier for us to apply it in the visible range. Normally, we work in the visible range, and then it is the second harmonic generation is observed in this crystal by illuminating light 1064 nanometer, and it will going to produce the light at 532, which is exactly the half of the wavelength of whatever the fundamental wavelength we have, and then we can generate second harmonic. So, here we have a picture here. So, if you look to this slide, there are many information that is dumped here. One is this is the picture of the crystal, and optics axis is also shown. Optics axis is a preferred axis along which we can define many things, and along optics axis the velocity of the ordinary and extraordinary waves are same. That means the refractive index along these directions are same. So, this is a very important direction for the axis, but here we also show one important thing, and that is how the second harmonics are generated. So, this is experimental figure. This is the experimental figure. If you launch a light around this, which is normally invisible because this is in IR region, this is. So, gradually what happened that in the output for KDP crystal, we will get a reddish color of light, which we say for the timing is a fundamental. However, fundamental light, if I launch it 1064, it is difficult to see because it is not possible to see with your naked eye. You need to put special thing to see these IR lights, but in the experiment we can do that, and this is the nature of the fundamental light. An important thing is that we can generate from this fundamental, the second harmonics are generated in the experimentally, and this is the second harmonic spot of second harmonic. So, I launch one light which is not in the visible range in the IR side, but whatever the light is generated is well in our visible range in the blue side, because the wavelength is near around 530. So, we will have a bluish light which is our second harmonic. Also, we can find out the refractive indexes, because the refractive indexes are very important, and these refractive index values are given here for the operating wavelength, say 1064. So, in 1064, if these are the refractive indices, this will be useful to find out the angle theta, this angle theta, because we have a expression of angle theta along which we have a phase matching, and this information basically help us to find out what is the value of theta. There is a expression, we have already derived this expression in our earlier classes, but the important thing is that here we have a crystal which is negative in nature, because n of O of omega is greater than n of E of omega. So, the velocity of extraordinary wave is the velocity of the extraordinary ray is faster than velocity of the ordinary ray. So, that is why it is a negative crystal. So, we know that in negative crystal Ne is less than No, except in this particular direction, which is the optics axis, where both the values are same. Well, after having the knowledge of KDP crystal, next we need to know with this crystal what we can do. So, here as I mentioned that we can able to find out what is the angle because in for KDP crystal we know that there is a certain angle at which the phase matching is achieved, and this is the example, this is the value of this theta. And if I now start putting this value in O of omega in O to omega from here at the operating angle at the operating wavelength, say 1064 nanometer, then we will find that this angle is around 41 degree. So, if I launch an electric field around 41 degree, this is the z axis and it is the x axis, then we should have a phase matching. Also, the D matrix of the KDP crystal is shown. So, here you can find that D matrix, there are only 3 non-zero components are there in the D matrix, and these non-zero components are sitting in this way: D14, D25 and D36. These 3 are non-zero components in the D matrix. So, we have the D matrix, we know along which angle the phase matching is there. These two very important information are there. So, now what we will do, we will try to find out what is the condition to generate the second harmonics in KDP crystal, or how the second harmonic is generated in the KDP crystal. So, before that we need to understand few things. So, let us understand what is going on here. So, here we find for KDP crystal 41 degree is the angle, preferred angle along which the second harmonic is generated, but we never mention that the orientation of the k, because k can be in zx plane and k may not be in zx plane, but still the angle might be 41 degree. So, if I look a more general figure, so one azimuthal angle one can assume which is referred here as a phi. So, in all cases, if this vector is rotate into this cone, one can make this cone. So, in this cone, for all orientation of the k, this angle is theta, because this is eventually a 3-dimensional figure. For 3-dimensional figure, we have a rotation like this. For all cases, this is touching with this this point is basically a round wise as shown here. So, all the points here over this circle, the value of the k is same, magnitude of the k is same, and the direction is changing because my azimuthal angle is changing, but interestingly the phase matching angle which is phi, which is theta here, is not changing. That means all orientation, the phase matching condition is valid. So, now question is, what is there any preferred direction of theta as well as phi for which we have a more value of the second harmonic more, or what is the condition to generate the second harmonic? Is it the sufficient? Is the angle is important? This phi is important or not? So, this is the spatial orientation of the k, where the angle theta is maintained here, but k is in zx plane. So, we start with this this condition and try to find out if k is in zx plane, really second harmonic will going to generate or not. That is the first thing that we will do. So, let us try to understand that. So, case 1, in case 1 what we have? In case 1 we have k is in zx plane. So, k is in zx plane, make an phase angle theta is 41 degree. So, this angle is around 41 degree and z is the optic axis. To achieve the phase matching condition around this OO to E system, that means two ordinary wave, they can merge and generate an extraordinary wave. So, the fundamental wave must be an ordinary wave. That is the first thing that we should look into, that what should be the fundamental wave, and this fundamental wave should be ordinary wave. because two ordinary wave can generate an extraordinary wave. This is the O plus O equal to E system, since the crystal is negative in nature. So, now the OA wave should be perpendicular to the z axis and k, that is very important. So, the orientation of the O wave, if this is O wave, it should be perpendicular to both k as well as z, the optic axis. The O wave is always perpendicular to k, propagation constant, the direction of propagation constant, and z. Here if you see that this is z, k is in this plane. So, if it is perpendicular to both, then the E has to be in y direction, which is perpendicular to this plane. So, now we know my P nonlinear is this, where E is this, P 2 nonlinear is represented by this, where half of P these things, I just write the old equation here, but orientation of the k is important. Orientation of the k, it is making an phase matching angle, but it is in x z plane. The question is, if this is the orientation, whether really we will going to get any kind of second harmonic or not. Okay. So, once we have the knowledge of my D matrix, it is readily, one can readily find out what is the matrix form of second harmonic, that we have already shown in this class. But before that, I can write that P I 2 omega tilde, that is the amplitude of the nonlinear polarization at 2 omega point, is equal to E j omega and E k omega with tilde, that means the amplitude of this. So, now if I try to find out what is the amplitude of the electric field for this system, we can say that electric field around x and electric field around z is 0. Here it is mistake, here should be z, E z. So, electric field is only along y direction, because if you remember the previous slide, k is along this direction, this is our k vector making an angle 41 degree, this is optic axis z, and in order to have the second harmonic, my fundamental wave has to be a an ordinary wave. So, this ordinary wave is perpendicular to z as well as k. So, that means it is along this perpendicular direction, and this perpendicular direction means it is along y direction, since it is x and z plane, it is along y direction. So, that is why E y is not equal to 0 here. So, now what we will do? We now know what is E x, E z and E y. E x, E z is 0. So, this is 0, this is 0, all the other terms will be 0. D matrix for KDB crystal is given. So, this is my D matrix, and P x, P y, P z is there. So, we need to find out what is my P x, P y, P z. Now, if I calculate this P x, P y, P z, we find an interesting thing that P x, P y, P z all are 0. That means, even though the k is launched along the direction for which the phase matching angle is satisfied, but still we are not getting any kind of second harmonic, because the matrix product. So, what is the conclusion here? Try to understand one by one. So, first we see that P x, P y, P z can be 0, even though the phase matching condition are there. So, that means launching of the k is very important, the azimuthal angle is important. If I launch the k vector along x z plane, but still the phase matching is there, but will that cannot ensure that the second harmonic will going to generate. So, the matrix product here, what the conclusion we have, let us check. The matrix product vanishes for the specific orientation of k vector, no nonlinear polarization of 2 omega. Since the k is in, as I mentioned, is x z plane, so matrix product is 0 here. So, P x, P y, P z is 0. So, no 2 omega generation can be possible. but you should note that the phase matching is still there. So, that means only the phase matching condition cannot ensure that you will going to generate a second harmonic. So, only the phase matching condition of the direction of k vector is not only, here should have a t. So, not only the phase matching condition, the direction of the k vector is equally important to excite second harmonic, as I mentioned. So, here we find that phase matching is there. I launch the k vector along the direction for which the phase matching is there, but azimuthal angle is very important, because I can launch the k vector in infinite orientation for which the phase matching is there, but the direction is different. Based on the k direction, one can know what is the direction of E ordinary and extraordinary, which eventually generate the second harmonic. So, in the next class we find that for KDP crystal, which should be the optimum direction for which we can generate the second harmonic. So, that means inside the crystal the direction is very important. If I launch the k in a direction for which the phase matching is there, that cannot ensure singly. So, this is not the only condition for generating second harmonic. We need to find out the azimuthal angle, that orientation of the k is really very important, for which I can generate or maximize our second harmonic. So, today we will going to conclude our class. So, we just started the generation of second harmonic in KDP crystal. One condition is shown where the k is in xz plane. So, in the next class we change the orientation of k and try to find out how the second harmonic will going to generate, and most importantly, if that is the case, how the D matrix will affect and what should be the effective D value, which value, because there are 3 different D values are there in KDP crystal, which D value is really responsible for generating the second harmonic, that is important. We need to find out that D value for which we are generating the second harmonic. So, with this note, let me conclude my class here. So, see you in the next class, where we learn more about the second harmonic generation in KDP crystal and about the orientation of the k and optimize the D matrix value. So, thank you for your attention. See you in the next class.